Hi, I'm Tianyu, and I'll be presenting tangent model composition for ensembling and continual fine-tuning. This is joint work with Stefano Suado at the UCLA Vision Lab. We first begin with the classical fine-tuning pipeline in deep learning, where a model, typically one pre-trained on a large dataset, is refined for a different downstream task. This leverages the priors from the source pre-trained model to save both time and resources necessary to achieve sufficiently good performance on a desired downstream task. However, data for fine-tuning is not always readily available in one monolithic batch. It can be distributed both across time and across models. The latter can occur, for instance, when models are trained in a federated or parallel manner, where a different model is fine-tuned on each different task. Given multiple fine-tuned models, we wish to deploy them at inference time. However, combining these separately trained models is not trivial. One effective method would be ensembling the outputs, or logits, of each model. However, this model does not scale well with the number of models in the ensemble, since the inference time increases with the number of models. Another recently proposed method for composition is model soup, where the weights of each individual model are averaged to yield a single composed model that can be queried at inference time. However, one cannot simply compose these weights or inner activations and expect meaningful outcomes, since there is no theoretical guarantee on the expected output of this operation. Instead, we propose to compose models which are fine-tuned in the tangent space of the pre-trained model. This is achieved by linearizing models about the common pre-trained initialization. This fine-tuning process yields models that exist on the same tangent plane, and which the outputs are linear with respect to their weights. This means that the linear combination of their weights is theoretically equivalent to a linear combination of the outputs. In other words, this would be the logit ensemble of these models. This method of composition is zero-shot and achieves the best of both worlds, preserving both the improved accuracy as a result of ensembling and the O1 inference time of weight averaging. In fact, our method, tangent model composition, even improves accuracy with respect to ensembling by 4.2%, while reducing inference costs by 2.5 times to 10 times in our experiments, due to imposing additional regularization on the fine-tuning process as a result of linearity. In our work, we explore compositionality in the context of continual fine-tuning, where tasks are distributed across time and arrive in a sequential manner. We show that by applying our method to fine-tune a different model for each task, and then composing them with the latest model in an inductive manner, we can ensure each task benefits equally from the priors of the pre-trained model, while ensuring generalization to all tasks via linear composition. We show that tangent model composition outperforms recently published continual fine-tuning methods almost uniformly on each continual fine-tuning setting: task incremental, class incremental, and data incremental, on a total of 13 experiments across 3 benchmark datasets, despite not using any replay buffer. Our method even outperforms replay-based methods, where we allow for a buffer size of between 2.0% to 8.2% of the fine-tuning dataset. Our method naturally yields a parallel training framework that fully compartmentalizes information obtained in each task. By simply sharding a dataset into several disjoint subsets, training can be parallelized across each shard and then composed as a final step in a zero-shot manner. Forgetting of each shard can trivially be achieved in a zero-shot manner by simply subtracting the weights of the relevant shard. For more details, please come and visit our poster at ICCV 2023. Thank you.